The Wolff rearrangement can be induced via thermolysis, photolysis, or transition metal catalysis. The reaction was discovered by Ludwig Wolff in 1902. The Wolff rearrangement has great synthetic utility due to the accessibility of alpha-diazocarbonyl compound, variety of reaction from the ketene intermediate, and stereochemical retention of the migrating group. The Wolff rearrangement has been used in many total syntheses. The most common use is trapping the ketene intermediate with nucleophiles to form carboxylic acid derivatives. Specifically, the Arndt-Eistert homologation, named after Fritz Arndt and Bernd Eistert, wherein a carboxylic acid may be elongated by the methylation. Another common use is in ring contraction method if the alpha-diazoketone is cyclic. The Wolff rearrangement results in a ring contracted product. The Arndt-Eistert synthesis is widely used nowadays for the synthesis of beta amino acid. Peptides that contain those beta amino acids feature a lower rate of metabolic degradation and are therefore of interest for pharmaceutical application. Before we look into Arndt-Eistert homologation, we need to know how to form diazocarbonyl. We start with carboxylic acid, add thionyl chloride, gives us our acyl chloride, and then add diazomethane, which will give us our diazocarbonyl. Step 1 is going to be Wolff rearrangement. Taking this diazocarbonyl, turning it into a ketene, either using heat, light, or metal catalysis. Step 2 is going to be nucleophilic addition. If we use water as a nucleophile, we get carboxylic acid. Alcohol will give us ester, amine will give us amide. So Arndt-Eistert homologation is combination of step 1, which is Wolff rearrangement, and step 2, nucleophilic addition. Let's look at the mechanism. So this diazocarbonyl, if I were to draw a resonance structure of this is what I'm going to get. A good leaving group and a carboanion. So this leaving group, which is nitrogen gas, is going to come off. We're going to form this carbene, a neutral carbon with valence electrons. Remember, it's not carboanion, it's a carbene. So now this carbene wants to form that carbon-carbon bond. So this carbon at the center of the carbonyl is going to have 5 bonds. So the R1, the R chain, the bond with that carbon is going to break and it's going to rearrange itself to this carbon, which will give us our ketene. Now let's use water. So water comes in, right, pushes that electron density towards that oxygen, giving us a protonated oxygen and a negatively charged oxygen. So proton transfer is going to happen. Now we form this enol. So that enol is going to abstract that hydrogen, right, forming this protonated carboxylic acid. So the last step is deprotonation, which was give us our carboxylic acid. So this is all for Arndt-Eistert homologation.